Welcome everyone back to geometry for one last video in section 26, coordinate geometry. The first thing that we want to take a look at is the activities for this section. The first one is verifying the mean concurrence theorem, and the mean concurrence theorem is given here. So it's a theorem that also came from section 21. It's not something that it's not something that we've seen before necessarily, but I think it's something that we are still capable of understanding. So make sure you read the theorem. If you feel like you need to, you can go back to section 21, but I do not believe that there's a need to. The main thing is make sure that you recall what a median is, which we did talk about in the section about triangles in Euclidean geometry. I believe that's where that appeared. It's possible that it appeared in the section on triangles, maybe a couple sections prior. Anyway, we've seen medians before, and all that we're saying is the medians are concurrent. That is, they intersect at one single point. When you're working through this, it asks you to prove the concurrence theorem, but to prove the concurrence theorem, we're going to have to use a generic triangle. So in order to do that, we want to ignore these labelings on the axes. And we want to give the points a better labeling, a labeling that is generic. So you might choose to do the same labeling that we did in the previous theorem. So you would have that B here is 2B comma 0, and that, excuse me, C is, let's see, you could call it 2A comma 2C. And then again, we want the midpoints. So M would be A plus B comma C, and down here P, the midpoint here would be B comma 0, and the midpoint here N would be A comma C. So you want to use that labeling when you write up your proof. Keep that in mind. All right, and then beyond that, we should be all set for that activity. We'll take a look at this theorem in just a moment, but I also wanted to mention the second activity in this section, which asks you to find the centroid, orthocenter, and circumcenter for a particular triangle. But these things, the centroid, orthocenter, and circumcenter, we did not discuss. Those are from section 21, and those are beyond what we have talked about. So I do not want you guys to complete this activity, not because you're incapable, but because it's just reaching a little bit beyond what we have actually discussed. You're welcome to attempt it if you want to. I'm not going to tell you you can't. You're welcome to refer to section 21 and then take a look at this activity. I just want you to know that with what we have presented, that it's a little bit beyond what we have actually discussed. So there's no expectation for you to complete this activity. So it should also not be included, not part of the homework. I believe it's listed as part of the homework to be submitted, but again, you do not need to submit this activity for the homework. All right, so let's take a look then at one last theorem for the section. So opposite sides of a parallelogram are congruent. We've seen this previously, definitely. Talked about a large theorem that had this as a small part of it, and we can use coordinates to help us prove this, that the opposite sides of a parallelogram are congruent. So in this case, we're beginning with assuming that we have a parallelogram, opposite sides of a parallelogram. Start with that. They are congruent. So to prove this, we want to create a generic coordinatized parallelogram ABCD. And as soon as we do that, then the proof that follows is incredibly short and very convenient. So let's give ourselves some axes here a second. Let's see, axes, and then go ahead and give ourselves some points. Of course, of interest, again, is to utilize the origin, so that way we're minimizing the values that we have to use. So 0, 0. And then let's see here, we can go out some ways on the x-axis and call this b, which would be at b, 0. So that's the same thing that we did for our triangles. But now the difference here is that I'm going to pick some point up here. I'm going to have 2 points up here. We'll call this one C and we'll call this one D. And we're just going to give these some generic points initially. Call it A, C over here and D, E over here. Okay. A, B, and C are all fixed, right? Maybe I could try to rewrite B in terms of the others, but I can, in particular, I definitely can rewrite D and E in terms of the other ones. So what we want to do here is we want to notice a couple of things. So notice, of course, since it's a parallelogram, that AB, line segment AB, is parallel to line segment DC. And so that tells us, let's see here, that the height in particular has to be the same for these two. So E is equal to C. So this coordinate here has C in the second place. Now, something a little bit less obvious, we'd like to say that we know what's supposed to be here, but it actually takes a moment for us to be able to say what it is. And I'm going to need a little bit more room there. There we go. So also, since we have that AD is parallel to BC, that tells us we have two parallel lines and that the slopes of those lines are the same. So the slope from A to D, or the slope of the line containing A and D, is equal to the slope of the line containing B and C. Why is that important? Well, that allows me to observe that the change in height, C minus 0, divided by the change in distance, A minus 0, is equal to the change in height, so E minus 0, divided by the change in run, the change in distance here. So that'd be D minus B. And we identified that E is equal to C, so that tells us we have C minus 0 divided by D minus B. But in particular, that tells us that D minus B is equal to A, right? Numerators are the same, so the denominators must be the same. A is equal to D minus B. And that tells us that D is equal to A plus B. So I only need 3 different values again, A, B, and C. I don't need D or E. And that's very nice for us. All right, so with that, the proof becomes quite easy. We already discussed how to calculate distances between points that are horizontal of one another. So that's an easy calculation. And then we already looked at how to calculate the distance between points. So, which will be, again, very convenient now with the location for C given in this way. All right, so using the coordinatized parallelogram, we have the distance from A to D. From A to D, we can use the distance formula on. So that's going to be the square root of A squared plus C squared in this case. Change in run, A minus 0, change in height, C minus 0, both of those being squared, take the square root. And the distance from B to C, again, the change in run squared plus the change in height squared. So that's going to be A plus B minus B. So square root of A plus B minus B squared plus C squared. But of course, A plus B minus B is just A. So that's the square root of A squared plus B squared. Sorry, A squared plus C squared. And we see that AD and BC are equal to the same thing. Telling us that AD and BC are equal, AKA they're congruent, right? Line segment AD and line segment BC are congruent. All right, also, the even easier calculation, the distance from A to B, since they are horizontal of one another, right? It's just a horizontal movement, no vertical movement. It's just the change in values, change in X values. So that's B minus 0, absolute value of B minus 0. Of course, that's just B. And the distance from D to C is the same, right? They're both the same height, so we just have to look at the change in X values. So A plus B minus A. So the distance from D to C, absolute value of A plus B minus A, of course, is equal to B as well. That is AB is equal to DC, and the line segment AB is congruent to the line segment DC, and that's what we wanted to show. So we're done. And that's it. And that is the end of the section for us. So if you have any questions, make sure that you stop on by during office hours, schedule an appointment with me, or of course, join us in class. I will see you guys later. Have a great day.